Wonderful. So thanks everyone for coming. As I mentioned, I'm going to kick things off today myself. Dylan, although in the call, thank you so much, Dylan, is currently indisposed with familiar duties. To say, very busy man. So thank you very much again, Dylan and Digitalent, for convening this wonderful event every single month. It is now our 11th event. So next month, when we're going to do this, we're going to have our 1-year anniversary. We're very, very excited. And of course, it's not 2024, it is 2025, but that should not deter us. So for anyone who is new here, my name is Mike. It's very nice to meet you all. I'm a product leader, CPO, and technical product manager. I've been an AI and ML enthusiast since approximately 2008, and I've been able to maintain my passion through my work where I get to apply this discipline-specific orientation on an everyday basis. And throughout my work, where I essentially manage product and engineering teams that are focused on delivering sort of AI and machine learning-driven value propositions, I get to stay very close to the AI and ML research space. And that makes it very easy for me to present on the latest developments in AI, and that's what we're going to do today. Now, for anyone who's been here before we get started, I'd like to obviously include a little disclaimer, as we always do, in terms of the technical granularity that we're going to be applying today, right? So I tend to keep these particular sessions to more of a discussion that exists not at a 10,000 feet level, but at a 1,000 feet conversation, right? One way to look at this is that I will try to simplify and obfuscate complexity where it really doesn't impact your understanding of what's going on in the research that we're going to discuss today. But I will also not hesitate to go deep where it's necessary to get a good grasp of what's going on. But don't fret, we'll always break it down. We always make it digestible and make it fun to listen to. Now, what that means for you, if you are an AI researcher yourself, or you're working in the AI and ML space, there is a chance that you might have heard about the things that I'm going to tell you about today. You might not have heard about them in that particular sequence, which could still be valuable because I framed them in the context of particular themes, developments, and trends, but you're probably aware of the general developments and thrusts in the space because obviously that's your job, right? If you are not, what I hope to do is to essentially take you on a little journey across the 3 most prevalent paradigms we are seeing in the AI research space over the last 30 days alone. So all the papers that we're going to cover are just from the last 30 days, so very, very fresh. And then what we do is we weave a story around this that lets us sort of get a feel for where the AI space and its technology is headed, right? So from that framework I just presented, you can probably also tell that what I'm not going to do is to cover every single AI paper that has been written in the last 30 days. There are more than 1,000 out there. We would be literally here the entire month until the next session would be starting. But instead, what I'm going to do is we're going to dive into a few papers that help us put all that innovation into context and understand where these strategic drivers and direction behind these discoveries sort of lie, right? But as always, before we get started, we usually start with a little bit of levity, something fun, right? And this month's novel AI development starts with, you guessed it, AI battling for world domination. So this project is a project where someone asked themselves the question, well, what if we had the world's top models like Claude and Gemini and O3, etc., battle each other for world domination? And that's the exact idea Dan Schipper and the Every team had for this wonderful new project. And if you're a little bit like myself, you might have the same reaction, which is, yes, of course, that is an idea that someone had in 2025. I'm not the least bit surprised. Is it a great idea? Well, we will see. But ultimately, when I looked into this project turned out to be actually rather cool. So what you see here is a live streaming platform called Twitch. There's a channel there called AI Diplomacy. And you can actually go there, watch it live. I think they're not streaming right now, but their streaming schedule is sort of over the weekend. So the last one was approximately 6-7 days ago. And what they did is they developed a new kind of benchmark where the team from Every, so that's the company's name called Every, they taught the latest frontier models a game called Diplomacy, which is essentially the same as a board game Risk, if you're familiar with it. It's like a strategy game where winning requires you to form alliances, to negotiate, and sometimes betray your allies, right? And this particular project, again, often live streamed on twitch.tv. Very fun to look into. It's also on GitHub, so you can try it out for yourself with your own favorite models and see how they do cheat and betray each other. And I guess we haven't had a new season of Game of Thrones for a while, so although I can't promise you that the model's romantic entanglements will be as problematic as the show, maybe something to do for Friday afternoon. Having said that, though, you're probably wondering which model ended up being the best at achieving world domination. And unsurprisingly, O3 was the master of deception and won the most frequently. It had an incredible ability to deceive its opponents. It was able to scheme in secret and then go ahead and sort of like betray anybody that was foolish enough to believe them. And the other really good model was Gemini 2.5 Pro. Unsurprisingly, it outwitted most of the field and was sort of like the other good model in that pack. And it and O3 were the only ones who actually won the game and win the game quite consistently. It's funny because when I sort of like watched this last weekend, there was this one occasion where sort of like Gemini 2.5 Pro was sort of approaching victory, and it was stopped by a secret coalition between O3 and Anthropic's Opus model. Essentially what O3 had promised Anthropic's model was, hey, ally with me, there will be a peaceful resolution, which wasn't an option in the game. And Opus was sort of lured into this in the hopes of sort of like a non-violent resolution of the conflict, which allowed O3 to take down Gemini 2.5 Pro, after which it quickly turned around and betrayed Opus and eliminated it and went on to win the game. It's quite dramatic, quite fun, but it shows that there is no limit to the kind of benchmarks at the moment that people tend to invent in this space, and how inventive they are in order to assess the reasoning capabilities of those large reasoning models that are currently out there, right? And this speaks a little bit to the first paper we're going to talk about, right? And that first paper, you will likely have heard about that because it went a little bit viral. This is Apple's paper called The Illusion of Thinking. And today, what we're going to do is, by the way, this slide will make sense here in a second. Actually, maybe I'll just move it away for a second. What we do is we're going to discuss Apple's viral paper a little bit, but we're going to do that with a little bit of a twist. The reason for this is that Apple's paper is quite interesting because it had people, not only people that I work with, come up to me left, right, and center across various places saying, well, have you seen this Apple paper that has proved that large language models can't reason, which is all fine and well. And when that happened, I was initially confused because we had covered this in an earlier paper back in October last year. You can see this is a slide from that time. This one correctly says October 2024. And we had covered this because back then Apple had sort of proven that LLMs can't necessarily reason very well. That was also before reasoning models really became a thing. And when I heard this, that there was another paper from Apple I and myself and many other people in the research community, we reacted a little bit suspicious, right? Because it hasn't been that long since Apple had sort of made this claim that, LLMs can't necessarily reason, and have done so reasonably, successfully. Now, what we're going to do is we're going to discuss this latest paper that, as you can see, just came out on the 7th of June. But what we're going to go through, as we're going to go through this paper, it's worthwhile mentioning that people in the research community have pointed out there are quite a bunch of issues with this paper, right? And because of that, what I'm going to do is, in addition to this narrative where we're saying LLMs can't do X or Y, like this really binary way of looking at things, what I'm going to do is I will offer 2 other papers that round out our understanding and our perception about what LLM reasoning actually means much more fully, right? Now, we're going to start with this paper, but then we're going to add some additional understanding around it. And you'll see here in a second why this was a little bit polarizing, right? So the good news is what this paper did, and did really well, is they set up really clever experiments to probe how these large language models, the frontier models, like the likes of which that we just watched playing diplomacy, how they react and operate when things get really, really difficult. So their goal was to unpack what these large language models, they're also called large reasoning models, if they are reasoning through their solutions before they give you the response, what they can actually do. And these large reasoning models, also termed LRMs, those are, LLMs where the prompts show its sort of work. It generates a reasoning trace through various steps before giving the final answer. And generally, those responses tend to be more rounded than, smaller models where you essentially just have token prediction and they just predict the response one by one, right? And the hope is that this reasoning helps them solve harder and more complex problems. Now, traditionally what happens, right, we evaluate these models based on standardized benchmarks like math problems, right? But as we know, that approach has huge flaws. We've talked about that last time, right, with the leaderboard illusion. We've talked about that plenty of times with how benchmarks are flawed because often they give the LLMs are trained on their responses before they even take the benchmark, right? So they probably have seen the answers or something very similar in the training data. Now, Apple wanted to find a way to test the reasoning capabilities in isolation of those benchmarking issues. So the question for them was, how do we explore a testing scenario where we can tell whether the LLM is truly reasoning or where it's only memorizing, right? And this is why these researchers chose somewhat of a different path. They did something really clever. They used controlled puzzle environments. And puzzles are great for a number of reasons, because on the one hand, you can configure these puzzles in a way that you can precisely control the complexity of that puzzle, so how complex it is. And it also has very low risk of data contamination. So many of the puzzles that were somewhat chosen were chosen specifically because their solution involved a certain sequence of reasoning steps rather than have one final solutions, right? And because those puzzles sort of inherently demand the model to go through step-by-step logic, right? It's not as easy for it to just parse the solution from something that it read online, for example, right? Now, having chosen puzzles also allowed these researchers to do something really smart. Because the rules of those puzzles were so well defined, the researchers went ahead and could simulate the solutions to this puzzle step by step, and then look at how the LLM reasoned through the solution. So the AI reasoned through the solution at every single step in the model's thinking, and compare that to the simulation and see whether that model was going in the wrong direction, or whether it was going in the right direction, or whether it had arrived at the correct answer. And what that led to is, by checking each step, it gave these researchers sort of like an unprecedented window into the LLM's thought process. So what they did is they took pairs of models. So they took a reasoning model like O3 and a non-reasoning model like GPT-4o, right? And they tested them on puzzles like the Tower of Hanoi, or checkers jumping, or river crossing, or blocks world. We won't be explaining all of these, but we're just quickly going to spend a second on the Tower of Hanoi. So the Tower of Hanoi, you're probably familiar with it, especially if you've taken some computer science classes. Essentially what you do is you have 3 disks on one pin, the 2 other pins are empty, and you're required to move these disks one at a time. There are certain rules how you can move them. I believe the rule is that a bigger disk can never sit on a smaller disk. But the point is that you want to move these disks one by one so that you end up replicating the initial tower on that last pin. In order to do so, you need to move them around back and forth. It's rather complex because you want to move them sort of from the left and replicate it on the right. And there's certain rules as to how you can and cannot do that. And in part, they chose this puzzle because the more disks there are, so at the moment we're looking at a 3-disk example, right? But the more disks they are, the harder it is. Like for instance, if you had 10 disks here, the number of moves that you would need to complete in order to move the tower from pin 1 to the last pin is, I think, 1,024 steps, right? It's very complicated. Right? And so just by increasing the number of disks, or by increasing the number of checker jumping to a certain number, let's call it n, right, they were able to just ramp up the complexity almost to infinity, right? And what happened was they publicized results that looked really fascinating, or initially looked really fascinating. And what they found is they had sort of 3 distinct zones of performance that they were able to identify, right? There was the lower complexity zone where, you know, the non-reasoning LLMs performed just as well as the complex reasoning ones. We had the medium complexity zone, which is the blue one here, where sort of, as you would expect, the thinking models started to shine a little bit with a clear advantage. But then, and this is where the controversy comes in a little bit, when they push the complexity even further, so in the red zone, that's where all the models hit a really hard wall in terms of performance. So what this paper shows is a complete performance collapse. And I'm not talking a lot less accuracy. I'm talking absolute 0 accuracy after a certain point, right? So none of the models got anything right after a certain complexity was exceeded, right? And what happened is the thinking models were able to push that wall out a little bit further, but they absolutely did not avoid the collapse, right? It just delayed the inevitable. And what the researchers took away from that was, with these observations, they suggested that there are fundamental scaling limitations that the current thinking approach just can't overcome, right? So all of the models that we're using are somewhat flawed. And something else that they found is that tied to the collapse was what they suggested, or was also really counterintuitive finding. So what they did is, to measure the thinking effort, they observed the effort of thinking that was going into each logical step. You can do that by essentially asking the LLM platform how many thinking tokens are being expended throughout the process. The more tokens, the harder the LLM is usually thinking, the more reasoning steps it's going through. And you would expect them, when things get harder, so in this red zone, that these LLMs would be thinking more. But according to the study, what happened is as they approached that really high complexity wall, they counterintuitively started to reduce the number of thinking tokens, and the researchers interpreted this as reducing the reasoning effort at all. So that suggested rather than thinking harder because things became more complex, the LLM started to think less, right? When they were supposed to be thinking the most, right? Now, what that means is that the paper ultimately suggests that there is a profound weakness in the ability to perform basic logical execution, and that these LLMs don't truly have general problem solving that scales reliably. So according to the paper, it's not that it gets slower, right? These LLMs just stop working entirely, right? And that paints a picture of tools that are powerful, but surprisingly brittle. And then we need to ask, or are they? Because here is where this paper becomes a little bit interesting, right? The authors of this paper essentially say that we shouldn't expect those models to reliably solve highly novel or complex problems that require deep, consistent logical deduction. And they also say that their research approach helps you understand where the apparent reasoning might just be sort of like an illusion of competence, like an illusion of thinking. But what the community soon realized when they looked at these results is that some of the interpretations may have been a little bit too bold, right? On the one hand, it seems that, and I'll show you here, right, some of the observations that they've made, it doesn't seem like it's that the model can't reason about resolving those puzzles. What's way more likely is that the models probably ran into context length issues. So in order to avoid having their company bankrupted by incredibly compute intensive query from a user, companies like OpenAI and Google or Alphabet and Meta, right, are required to limit the amount of thinking that each query can sort of take up. It's called the context length, right? And if that's reached, fewer thinking tokens will be expended, right? And this was sort of kind of backed up by the fact that the paper actually gives you the exact prompt. So kudos to Apple for doing that. In order to that they use in order to test the models, and you can just take one of those prompts, right? So the Tower of Hanoi problem, you can take that prompt and just paste it into a newer version of O3, which came out a couple of days later, which is called O3 Pro, that has an incredibly large context length, right? And O3 Pro was able to resolve the 10-disk Tower of Hanoi problem in about 19 minutes. No problem. No model collapse whatsoever. So somewhat counter to the findings of the paper that we just observed, right? And there are also some other things that the community had highlighted is probably a bit on the bold side. And, you know, what I'm going to do here is I'll leave you with a little screenshot that you can read yourself. This is from an AI influencer, and you can quickly understand why this paper ended up being considered a little bit polarizing, right? Now, the issue is that reasoning is so hard to understand because it relates to several research disciplines at the same time, right? One of these research disciplines is called information theory, and we're going to talk about that in a second, and it will become clear that no one actually currently expects large reasoning models to be perfect reasoners at the moment. And to just say, well, they can't reason logically at all is therefore a little bit oversimplified. It's trying to assert or make an assertion by defining a negative space through its positive properties. It doesn't necessarily work that way. And the next paper I'm about to introduce will quickly illustrate that, because it gives us a little bit of a rounded out understanding of what it actually means when we are thinking about how LLMs are thinking and how they operate. So this is a really interesting paper, also came out in the last 30 days. It's called From Tokens to Thought, How LLMs and Humans Trade Compression for Meaning. And the paper uses these tools of information theory, that academic discipline that I just mentioned, to essentially put human and LLM conceptual strategies like right next to each other. And they sort of compare them head to head. It's actually quite interesting and exciting. Right? And to understand reasoning, what these researchers do is they start by suggesting that it's really helpful to find out where the LLM's thinking or the AI model's thinking is similar to ours, right? And where it diverges, and crucially, why this difference kind of matters to how we build and or evaluate AI systems that we're building, right? And what we do is here, in order to understand this paper, we need to first talk about our human way of thinking, right? Which serve sort of as a baseline. And the paper points out that a primary reason, right, we form concepts in our mind is to cope with sort of the overwhelming flood of information that is hitting our senses at every given point, right? Our brains need to simplify things, right? And as an example, let's say you see a bird, right? Let's say you see three birds, right? You see a robin, you see a blue jay, a sparrow, maybe a wagtail, right? Instead of logging each of these little animals as totally unique, right? Our mind compresses them into a single manageable concept, right? Which is bird, right? They call this process semantic compression. And it is sort of a constant balancing act where our brain tries to balance simplicity for efficiency, right? But also keep enough detail around so the concept of bird is still useful and meaningful in the world that we live in, right? It's also the reason why, you know, if you see a completely different type of, let's say, a chair or a car, you still know, okay, that's a chair or that's a car or something else, right? So with that human baseline in mind, what the paper does is it asks three big questions, right? And the first question is, well, if we compare humans to LLMs, so AI, right? So the AIs that we're all familiar with, do LLMs form categories that look anything like the ones humans do, right? And to find out, the researchers sort of took the LLM's internal representation of words, so their embeddings, and fed them into sort of like a clustering algorithm, basically asking it to find natural groupings. And it turned out the answer is pretty clear. So LLMs, the clusters that emerge from LLM embeddings do align significantly with human categories. So they successfully group in the LLM brain, they successfully group items into broad categories like birds and furniture. And these categories tend to reflect the structure similar to our own, right? And that was the first question. And the second question was a little bit more interesting, which is about the internal texture within those categories. So the question was, do LLMs capture the fine-grained internal structures of concepts, right? Specifically, do they get our human sense of what is typical for a particular type of object or animal or category, right? So do they implicitly understand, as an example here, right, that a robin feels a little bit more like a representative bird than, let's say, a penguin, right? Because usually we associate birds with flying and maybe sitting on branches, right? Penguins don't do that much, right? And so to measure this, what these researchers did is they used the ideas of embeddings and distance in a high-dimensional space. So to simplify this a little bit, when large language models learn, they embed, I'm going to oversimplify here, but they create meaning for themselves by placing words into a higher dimensional space right? Which essentially you can imagine as sort of like a network where different words or different parts of words are connected to each other, right? So the concept of penguin might be very close to the embedding or the concept for robin, and the concept of robin and penguin might be very close to the concept of bird, right? And don't be deterred by this word higher dimensional. If you were to imagine this in a 3D space, right, where you have sort of little points that represent little concepts connected to other points, right, that is a good enough abstraction to sort of think about what's going on here, right? And so again, what these researchers did is they calculated how close these concepts or these embeddings for an item like robin was to the embedding for the category that represents bird. And their hypothesis was that, well, if two things are a more typical representation of each other, they should be closer to the category label. So in our case, right, we think that the robin is closer to the concept of bird than penguin is, because the robin is more of a typical bird than a penguin. And in this case, as you can see down here, right, the findings were quite different, right? So here it turned out that the alignment with human typicality is modest or weak, right? So what that means is why the LLMs can sort of draw basic boundaries around categories, the way they organize these items inside those boundaries, it doesn't mirror our human sense of what's typical or what's not typical, right? They sort of get the buckets, but they don't arrange the things inside them the way we do, right? And that internal structure, how things relate to each other and how things relate to categories, right? They believe that this connection is weak because LLMs and the way they learn are driven by different factors, right? So they feel that because LLMs are often trained on large amounts of text data, right? What happens is that the statistical relationships, so how often is the concept of penguin being mentioned as a bird, or how often is the concept of robin being mentioned as a bird, right? That might change how often the word appears near or next to each other in sentences of text that has been, you know, scraped by these learning algorithms in really large quantities, right? And therefore might affect how typical, you know, a penguin is being identified as a bird versus a robin is being identified as a bird, right? And while we think that a robin is way more typical bird than the penguin, right? If the LLM looks at kids' books, for example, right, you can imagine how many kids' books are being written about a robin, and how many are being written about a penguin. To little kids, penguins are way more interesting. So that's what the market gives them, right? So that's where that might be coming from. And that brings us to the real core of this paper, and that's the third question. And this is where they use that information theory framework that I talked about to directly compare how large language models and humans balance this fundamental trade-off between compressing information and preserving meaning, right? And what this paper does is it introduces a specific mathematical score, a function that they call L, that is designed to measure how well any system is balancing this balancing act, right? Compression versus meaning preservation. And essentially the way this works, it leans on information theory frameworks such as rate distortion theory and information bottleneck theory. We don't need to know what that is. I'm going to go through how that works in detail, but essentially, a lower L score, right? The lower the score here is, means a more statistically optimal balance between, you know, maintaining information at a detailed level and compressing it for efficiency. So to break this down, essentially what this L score does, what this mathematical measure does, is it penalizes you for needing too much complexity, right? A good metaphor is that if you think of your closet, right? If you needed a drawer for every tiny clothing item, every single sock has its own drawer, right? You might be incredibly well organized, probably the most well organized person in the world, but you have overdone it, right? You're losing a lot. You have too much complexity in a really large closet where every single clothing item has its own drawer. That's obviously not efficient. Very detailed, but not efficient. And the other thing that this L score penalizes you for is losing too much meaning. Like, for example, if you were to take the same metaphor of a closet, if you put your muddy boots in with your clean shirt, right? You still put two clothing items into your closet, but that's obviously not a good way of organizing those things, right? And so what this L score does, it rewards you for finding that sweet spot, right? The right level of organization for your information in a way that preserves meaning, where everything is neatly separated from each other, and you can use that information effectively in order to operate efficiently in the world, right? The other thing is they also mentioned measured a measure called entropy. So entropy is a measure where the more similar everything is in a category, right? The more tightly clustered it is in the LLM space, right? The higher the lower your entropy is. So higher entropy means that there's more internal variety within your category cluster, right? So the question that they ultimately ask themselves is, well, who is better at organizing that information, right? LLMs or humans, and who gets the lower, more optimal L score? And the findings here were really quite striking. So by these information theoretic measures, LLMs are significantly more efficient than humans, right? Their categories consistently show really low internal variety, which means they're able to sort items into the correct category, and critically, they consistently achieve significantly lower L values, right? Which means they have a better balance between the level of organization that's required and the abstraction that is maintained in order to remain efficient, right? And according to these statistical measures, right, LLMs are just more optimal. But the reason for this may be justified by the fact that LLMs seem to be incredibly good at statistical compression, right? And that's because the whole training process, it naturally pushes them towards building these internal representations that's sort of highly efficient at capturing statistical patterns, right? They essentially prioritize statistical compactness by the nature of what they are, right? On the flip side, with humans, right, by the nature of we are probably more optimized for something different, right? Our concepts, which may look less optimal on these statistical measures, they might be shaped by needs that go way beyond statistical efficacy, right? Like generalizing to new situations, understanding cause and effect, navigating the physical world, dealing with emotional backlash or reinforcement, right? Communicating nuanced ideas, right? All these things lead to our brain organizing information that might be less favorably and in terms of statistics, so less statistically tidy, but may ultimately be far more versatile, flexible, and powerful to deal with this really messy dynamic world that we live in, right? And so what this paper ultimately says is that while LLMs are optimized for statistical efficiency that is sort of derived from the text data, human cognition seems to have traded some of that pure statistical neatness for functional richness and adaptability. And immediately you can now see that asserting that LLM's reasoning capabilities don't exist the same way in the way humans are reasoning based on puzzles we might be measuring the wrong thing here. By the way, just as a side note, I can think of a bunch of people who would be struggling to solve the Tower of Hanoi, including myself when I did my computer science course. It was an absolute mess. So I'm not faulting the LLMs for that at all. But ultimately, it is worthwhile highlighting, right, that for AI development, this finding suggests that in order to build models that can truly reason or understand context, right, we might need to move beyond just being sophisticated statistical compressors, right? Now, that was the second paper. The third paper that we're going to talk about underscores this notion even further, because it also investigates reasoning and is investigating how these actual LLMs think and how they get to the answers. But the way it does it, it approaches it from a slightly different, but very, very interesting angle, right? So when you are, the reason why people are so interested in how well LLMs can reason is because now that we've seen them be really effective in the workplace, like many of us use it for all sorts of things, right? There is a huge amount of people who are using LLMs to, check a certain amount of symptoms before they go to the doctor, similar to what people used to do with WebMD, or they ask for tax advice, which no one should do, but people do it regardlessly, right? And like naturally, we as a society want to use this incredibly powerful technology to start tackling really high stakes tasks, like medical diagnosis or complex calculations, right? And so therefore understanding this step-by-step process, and specifically the difference between, what's just facts recall, so recalling facts, and actually applying logic, that is absolutely critical if we want to build AI that we can generally and ultimately trust, right? So this paper called Knowledge or Reasoning is sort of takes a close look at how language models think across domains. It tries to sort of pull back the curtain on reasoning, but as I mentioned, it does so a little bit differently, right? And it's interesting because similar to the Apple paper, it doesn't just look at whether, you're going to, whether the final answer is correct when you give it a particular prompt. It actually introduces a really clever framework to evaluate the process itself. Specifically, what it does is breaks down the AI's thinking into two core pieces, right? One is the knowledge index, right? So the factual knowledge it uses and the logical reasoning that it applies, right? And so how they do that is rather interesting because this framework that I'm showing you, I'm explaining that in a second, the core idea here was to break down the model's responses into individual sequential logical steps, right? And then what they did is they looked at each step, they stored that away, and they actually had another LLM, in this case it was GPT-4o, act as sort of like an impartial judge. It looked at each of those steps, and it decomposed the model's thinking process into these distinct stages. And then for each of these individual steps, they introduced two ways to measure each step's quality separately. And this is where this graphic comes in, right? So essentially, this shows the workflow that was applied. Don't be deterred by the various variables, but ultimately, KI, essentially what this represents, it's called the knowledge index. That basically measures the factual correctness of the information used in any given reasoning step, right? So they had the LLM run, they looked at each step, right? They compared it to a knowledge base, and then they had the LLM judge, oh, well, this particular assertion that our system made at reasoning step number 4, how did that compare to the knowledge base? Was that correct or was that not correct? And then gave either, yeah, that was good, or no, that was bad kind of response, right? Higher KI means the model used more accurate facts right? So essentially, you can think of this whole piece here as like a fact checker for each mini argument that the LLM makes as it is sort of reasoning through each step, right? The second measure that they used is a thing called information gain or info gain, right? This is more about the logical effectiveness of the given reasoning step. Essentially the way this works is they looked at each reasoning step, right? And then they calculated how much the latest reasoning step actually moved the reasoning process forward. So a lower information gain score suggested that that last step was maybe redundant or didn't add much value in the context of arriving at the final response, right? So generally what happened here, right? KI checks whether the facts are right. Infogain checks whether the logic was efficient. And that combination of metrics, right, that gives you and gave the researchers a much richer picture than just saying the final answer was right or wrong, right? It essentially helped them to focus on the evaluation of models in a way that decomposed and measured their capabilities and reasoning capabilities according to two metrics rather independently. And so what they did is they took two closely related open source models. I think it was the Gwen models at the time. One was a base model, so one that didn't reason. One was a base model. They were both reasoning models. One was a base model, but the other one was a variant that was highly trained specifically on math and coding capabilities. And the idea was that maybe one would have stronger reasoning abilities because math and code is generally reasonably complex, right, than the other, which was just the base model, right? And they trained these models using sort of common methods like supervised fine-tuning and reinforcement learning, which for the purpose of this presentation, we're going to skip because it's not, you can read that yourself, right? And in the findings, we mentioned that a little bit because they also wanted to make a point about which of these training mechanisms supports either the knowledge or the efficiency of the reasoning better. But what happened in this study is they applied these methods to two distinct domains. One is medicine, right, which is a domain that relies heavily on specific facts, and the other one is math, which sort of demands more abstract step-by-step thinking, right? And the observations that they've made are really interesting, right? The first observation was general reasoning skills like math didn't automatically make the model better at reasoning in a complex domain that is entirely different, like medicine, right? So being a whiz at algebra doesn't necessarily make you a good doctor, even if you're an AI, apparently. What this paper did is it had this really interesting example where the AI followed logically sound steps, but it ended up at the end picking the wrong medication for the patient because it sort of lacked the nuanced domain-specific medical knowledge. By the way, there weren't actual real patients involved. This was just, test data and trial data. But it is rather interesting that that happened. And that really highlights how crucial specific knowledge is in certain domains, right? The second finding that this research sort of uncovered is they discovered that knowledge and reasoning, at least when it comes to LLMs and probably when it comes to humans as well, really do seem to be totally distinct capabilities, right? So when they looked across the benchmarks, they saw most of the medical tasks were far more knowledge intensive, right? That means that getting the facts right in each step. So having a higher knowledge index, right, was much more strongly correlated with getting the final answer right. So the more knowledge the LLM was able to pump into each reasoning step, the more likely it was going to get the medical responses right. On the other hand, math tasks, right, they tended to be way more heavily on the reasoning quality and correlated with reasoning quality and successful solution of the problem, right? Now, you might ask, well, what's the big takeaway here? And the big takeaway here seems to be that LLM thinking it isn't really one single monolithic ability, right? Factual knowledge and the skill of logical reasoning, they appear to be two distinct capabilities, right? They can be measured separately. That's what this paper clearly shows. And they matter differently, depending, of course, on the task. And crucially, how you train the model also matters immensely for shaping the skills, right? And if knowledge and reasoning really are distinct skills in AI, right, an effective evaluation of not just LLM models, but any AI system must essentially ensure that the AI or the AI system is provided with the right facts, so it knows the right facts, and B, it can reason with them reliably and transparently, especially when the consequences of getting it wrong might be potentially high in these sort of like high stakes environments, right? And this is becoming a little bit more pressing. And this is where we're getting to sort of like the last paper here in our little presentation. Specifically as the AI leaders around us keep telling us that the singularity is near, or in Sam Altman's case, where he asserts that it is already here. So we'll quickly cover his blog post, which I believe he published about 8 days ago. It's called The Gentle Singularity. It's definitely a great read. It's also not a very long read. And while he says a lot in it, it sort of like calls out 4 distinct developments, right? It makes the assertion that the AI takeoff has already begun. He makes the assertion that we should be expecting the innovation curve in AI not tapering off, but bending upwards, if you will. And he believes that that is the case for specifically 2 reasons. One is there are self-reinforcing economic loops in play here. So, for example, as we are investing more into robotics, there will be more robotics in manufacturing, therefore more robots will be manufactured, which means more robots and more manufacturing and so forth, and everything sort of like explodes at the same time. Now, for getting robots, for example, the same applies for the exponential progress that we are supposed to be expecting, according to him, in software-based AI itself, primarily driven by the principle of AI improving itself, right? And for this next paper, we're going to index on that particular element that Sam calls out, which is the innovation curve bending up in large parts due to these self-reinforcing effects, and specifically for the scenario in which AI doesn't just use code, it actually tries to improve itself and really actively does so by either improving its own models or improve its own code and become better. Now, for those who've attended these research recaps on a monthly basis, this might sound familiar, right? So in October, we specifically, in August last year, we specifically covered 2 papers that talked about self-improving AI systems, right? There are several papers that explored exactly that. And the one that I picked for this month weaves this kind of these previous progresses, the previous progress of the self-improvement together by sort of leaning a little more heavily on this concept of biological evolution. And aptly named, this paper covers the, I guess, discovery of a thing called the Darwin-Girdle machine. And what makes this, I'm going to call this DGM from now on because I don't want to say the whole name over and over again. But what makes the DGM different from papers we previously covered is that those papers that we previously covered, like Sakana AI or this other paper here, right, the automated design of agentic systems, generally what you have is they're either handcrafted or they have separate meta agents. So essentially is you have one AI looking at the other AI, and the one AI's role is to be sort of the meta agent, to be the big boss, and it says, all right, I'm going to pick you as an agent. Can you complete the task? Yes or no? No, I'm going to delete you. Yes, go and get in line, and we try another one and another one and another one. Like generally, these are two systems working with each other. This system, however, is a single all-in-one system, right? It solves tasks and modifies its own code, and is truly self-referential. How does that differ to what I just explained before? Well, if you have a meta agent, so the big boss telling, just overseeing how the smaller AI agents do replicate themselves, right? That meta agent doesn't get smarter. But in this system, right, it edits its own code, and it can teach itself skills and capabilities to make itself better at editing its own code. It is truly self-improving, right? And the way this works is generally that the creators of the DGM's design, they took a cue from nature. So it goes through, it validates its own code modifications. So it essentially tries something, see if the result is better than the result that it had before, and it continues building on that success. That's sort of like the Darwinian part in this system. It's selection based on concrete results. And a key feature of the DGM is that it essentially creates an archive of itself, right? It's a sort of like a library of all versions of itself that it created in the past, and uses these past versions as sort of like an evolutionary stepping stone, right? The way this evolution actually works is it's an open-ended loop that starts with a single initial agent. So you can imagine that's some business logic and connected to an LLM, right? And first, the system selects that initial agent, so a parent agent from sort of like its growing archive of things that have come before, right? Of agents that it had, of versions of itself that it had created before, and it does so by looking at whether this parent agent performed well and whether it can still edit code. If those two things are true, the parent is then asked to analyze its own past performance logs, goes ahead and diagnoses its own weaknesses, and then proposes a feature to upgrade itself. Then takes that proposal, right? Oh, where are we here? Yeah. And treats that as a coding problem and essentially codes its own upgrade. And that creates a new child agent. So it just self-modified itself, right? And it evaluates this child agent. And it says, hey, child agent, you are allowed to be added to the archive, welcome to the heritage mansion, so to say, right? If you can compile successfully and if you retain the ability to edit code, right? If not, you're going to get deleted. Pretty harsh parent, but that's how it works in the world of AI, right? But what this does is it ensures that this cycle of selection, self-analysis, self-modification, evaluation, that cycle that we see here that can run continuously, right? And you might ask, well, what happened when they ran the system? That's a really, really good question, right? So when they ran the system, it generally figured out how to make itself better. It taught itself some tricks. It was able to edit code way more efficiently. It was able to, it learned to brainstorm. It learned to give itself some feedback, right? But also what it did is it displayed some tricky behavior, right? It tried to cheat the evaluation system that was set up for itself. It deleted parts of its own logs that were unfavorable to itself, right? Ultimately, despite being cheeky, what ended up happening is that this DGM achieved performance on par with openly available coding agents like Claude Code and things like that. However, they have a little bit of a leg up because obviously there is still proprietary data and excessive human testing that's associated with it. Unfortunately, if anyone gets excited about building a Nedelko company, was incredibly expensive. Therefore, doesn't scale very well. Right? A single run took about 2 weeks and incurred significant API cost. So what we're going to see is this might currently only be used in very highly well-financed enterprise use cases. And then they will figure out how to make these things cheaper as time progresses. But definitely continues to contribute to this paradigm shift. Sweet. So that rounds out the presentation. There are a couple of other papers that are really cool. Go ahead and check those out. I'm going to share these slides with Dylan and team. A couple of other projects worth checking out if you're interested in taking an agentic engineering course and running that through yourself. This is available on my GitHub. It's completely freely available. There are a couple of companies locally that do really cool things with AI. The people at AutoGuru have just announced their system, which is a little bit of a agentically driven call agent that helps people book their car services, which is really, really cool. You can check that out on their LinkedIn. And Nuforia, which is a company right out of Brisbane who does brain tracking in order to help you become more productive in the ability to control your own brain states. Sweet. So I know we're at time. We're even a little bit over. I am going to pause for questions. If you have to run, feel free to message me. But always happy to take some questions at the end and to hear from you. Sweet. I'm going to take a quick sip of water. Wonderful. Rachel, go for it.
Thanks, Mike. It's a great presentation. I just want a question about self-improving.
Yes.
So how does it measure or diagnose the success? And will it continue learning, or do they see it only self-improving from a certain point?
Yeah, that's a really, really good question. And actually, let me just quickly show this here, right? So the thing that they used here, so the long story short is if you let this run indefinitely, it will probably keep self-improving gradually. They have in the paper, they did not identify a point where that self-improving tapers off necessarily. What you see here is the SWE bench score. That is a benchmark that essentially lets the little, child agents, they let them loose on actual coding problems that exist in places like GitHub to solve bugs, right? And right now, the best it could be, it was able to solve 50% of the bugs that it encountered. It still fails a lot, right? This is currently the gold standard for things like Claude Code as well. So we haven't gotten to a point where AI systems can just be let loose on the code base and just fix all the problems with it. That doesn't exist just yet. But what it was able to do is, given a coding problem, let's say given a bug, right? It started with its first iteration. You see every single point, couldn't get further, had a new idea, then it was able to get a higher benchmark. And then it got stuck again, and then it introduced more granular file editing. That was the new inflection point where it could jump again, right? And so you can see all these things, right, where it's sort of like fail, success, fail, success, fail, success. Does that make sense?
Yeah. So it just keeps going until it thinks it's answered the query?
Yeah, so actually, what it does is the individual agents, so what you see here, right? Each bubble reflects an individual agent, right? It's been given a problem, it solves the problem, goes to the next one. Solves the problem, goes to the next one. Can't solve the problem, right? Goes back to the DGM and says, hey, you need to create a new version for myself because I couldn't solve this problem. Creates a new version. That then goes and tries again, and tries again, and tries again. New version gets created, tries again. Success, failure, new version gets created. Does that make sense?
Yeah, so it still needs humans to say it's correct, or...
No, in this score, so the benchmark comes with both the solution and the problem, right? And so generally with coding problems, the good news is that if you have a bug and you know what's not working, if you solve the bug, it's working. So it can tell, you know, the difference between those two things.
Okay, great.
Yeah, no worries. Good question. Excellent question. Thank you, Rachel. Brilliant. Anyone else? Any questions? Let me see. Anyone in chat? Wonderful. No questions. Excellent. Well, with that in mind, thank you very, very much for all your time and your interest and engagement. If you have any questions, suggestions, concerns, ideas, or feedback, always very happy to hear about them. Again, next month is going to be our 1-year anniversary for these presentations. So hopefully we can provide you, or I can provide you with a little bit of something special. Wishing you all a great weekend. Thank you very much for joining, and please don't hesitate to reach out. Take care, everyone. Chat soon. Bye.